Okay, so in this video, we're going to look at how to calculate the work done by winding up a chain. Now, one thing to mention is that occasionally these problems will also have you wind up a chain with maybe a ball, like you've seen the ball and chain type things, and when cranes are knocking down buildings and things like that. The ball itself does not have to be included in the integral. You can do that traditionally by the work equals force times distance, because you're going to treat the entire ball as a solid object. Now, it can be included in the problem as just a plus a constant after you figure out the force for the chain portion. But you can also just do it separately and just make sure that you add it on. So I'm not gonna do an example that includes the ball, because it doesn't have to be done by this integration method. What we're going to focus on instead here is we're going to focus on the chain itself, because as you wind up the chain, once you wind up the chain part way, then the weight that you have to wind up, the next turn of your whatever you're winding it around, there isn't as much chain to pull up. And so as you wind up the chain, the weight of the chain that you have to wind up gets smaller and smaller. And so therefore you don't have to spend as much force, because you don't have to bring the entire chain the same distance. The top of the chain doesn't have to go as far. The bottom of the chain does have to go as far. And so it's not a constant, that it's not like it's all lying on the ground and you're just picking up in a big pile. So that is why we have to do integration for this problem. Now, chain problems can have other kinds of scenarios. Sometimes you won't wind them up, but you will only carry them up. Maybe you only pick up the bottom of the chain and pull just the bottom of the chain to the top, and you want to know how much work is done in that case. You can think of the chain scenarios in that circumstance somewhat similarly, but the way that you get the formula is going to be a little bit different. Okay, so there's different ways to sort of set up these problems. It depends a little bit on how you specify your unit. So where is your zero? Where is your sort of maximum height and distance? And so depending on where you set those, sometimes the problems can look a little bit different. But let's look at this particular scenario and the way I've done this. So we have a chain that's 200 feet long. It's hanging from a crane. We're setting the chain to weigh 14 pounds per foot. So it's a pretty heavy chain. Calculate the work done in winding up half the chain. In other words, winding it up so that it's 100, the bottom of it is not on the ground, but it's 100 feet up off the ground. Now, the way that we have to figure out the force for this problem is that the force is the density of the chain times the length. But again, the length that the chain is moving, the piece of the chain is moving, is not constant. So what we have to figure out is, what is the force per unit length, essentially. And so the density is the 14 pounds per foot. The fact that it's per something is telling us that that's the density. And then the length here, we're going to calculate dy. So again, think of it as this is the per length component. So dy is a small unit of length. If you're thinking of it as 2 feet, then it would be 14 times 2. But if you're thinking of it as a half a foot or a tenth of a foot or an infinitesimal part of a foot, it's 14 times that little infinitesimal part of the foot. And so again, we're thinking about this very small slice of the chain, and how far does that very small slice of the chain have to go? And then, again, remember, as we set up our integrals, we're thinking of these as little pieces that we then add up. So it's 14 times however large our little slice of the chain is. Now, for a segment of the chain at height y, so y units above the ground, that piece would have to be wound up 200 minus y feet. So again, if you're at the very bottom, so think about this. If you're at the very bottom of the chain, so 0 feet off the ground, then this would be 200 minus 0. And so the very smallest end of the chain would have to be wound up the entire 200 feet. But if you're halfway up the chain, so you're 100 feet off the ground, then that portion of the chain, if you were to wind it all the way up, would only have to go another 100 feet to get to the top. So that's why the 200 minus y, I'm setting, this expression requires that I'm setting my 0 at the ground, at the bottom of the chain, and 200, which since the chain is 200 feet long, that's the top of the chain. Now, if you reverse this, if you set 0 to be at the top and 200 to be at the bottom, then your formula would become just y, which is easier to integrate, but mathematically, I like to think of 0 at the bottom and 200 as positive value. So that's the way I've set this up. So our force unit is 14 dy. Our length, the distance each piece has to be moved, is 200 minus y. So we multiply our force times our distance together. And then we integrate from the chain is fully extended at 0. And then we're winding it up to 100, 0 to 100. That's our limits of integration. And then we just do the math. We pull out the 14. We integrate 200 minus y. We plug in our 0 and 100, and we end up in this case with 210,000 foot-pounds. Again, foot-pounds because we started with 200 feet of chain and 14 pounds per foot. Now, if you are in the scenarios where you are, say, maybe only pulling the chain up halfway, the hard part, the part that differs, is getting sort of this portion of the problem. So how much is that weight changing? The force density times length component, that portion still basically is the same. It's the distance traveled that you kind of have to worry about. And generally you want to think about, essentially you're folding up the chain. So I find it helpful in order to come up with your formula to think about what happens if I fold up 1 unit of the chain, and then what if I fold up 2 units of the chain? What is the height that I've traveled to? And then use that information to come up with a formula. It can be helpful to plot the points. It can be helpful to find 2 points on that line and then find the equation of the line between the 2 points that way. It's usually when you're folding up half the chain, you're going to have 2y in there somewhere, because if you fold up 2 feet of the chain, then that tip of that chain is now basically twice as high off the ground as it was before. So if you fold up 1 foot of the chain, right, you fold it so that it's basically pointing in the opposite direction, the very bottom of the chain, if that's 1 foot off the ground, because you pulled up that 1 foot of chain from the bottom, the very tip of that chain has actually moved 2 feet. The place where the chain is bent hasn't moved at all, but you've moved that bottom end, not just up to the 1 foot level, but you've moved it up to the 2 foot level. And then if you fold up 2 feet of chain, then again, the place where the chain bends is 2 feet off the ground. But now what was the tip of the chain has not just gone up to 2 feet, but now it's gone up to 4 feet because it's 2 feet above where you've bent the chain. So using that information, usually that will get you that piece of the formula. You're not just wrapping it up by one y at a time, you're wrapping it up by 2y. But generally speaking, this is the procedure for setting up your work problems involving chains. And as I mentioned before, if you have a dead weight on the bottom of the chain, you can just add it onto a constant outside the sort of force expression here. Or you can just calculate it separately and add it on at the end. Next up is tank problems.